Okay, I think we're ready to begin. So let me introduce myself. My name is Jason Bradshaw. I work here in the College of Liberal Arts and Sciences in the Office of Student and Academic Programs, which is part of the Dean's Office. And I'm a management research analyst senior. I handle enrollment management for our ASU Online and also do general data analytics. Today we're going to talk about exploring and validating undergraduate advising data. Now, the initial title of this presentation had using Alteryx at the end of it, but it's not as Alteryx centric. There's more to it than that. So I sort of removed the Alteryx piece, and I'll show you the Alteryx workflow I use to sort of compare some of the data that you'll see that I'm just going to display throughout the presentation. So some background and context. In 2018, the College of Liberal Arts and Sciences moved to Armstrong Hall, and part of that move, we introduced a centralized advising, or what we call the hub model, for mostly our new first-year students. And as part of that model, all of our first-year students are tracked and remain with an individual hub advisor throughout their first year, provided they remain in a plan within the college. We also touch new transfer students and new transfer students in the college have an initial advising contact in the hub as well. And then after that, they're transferred to their primary academic unit, usually before or during the first semester they are enrolled. Part of the move to the hub introduced a need for new types of student-centric data that incorporates the advising data we're going to discuss today. So the focus on this will be primarily on just one advising table in the data warehouse, but there are at least three. And at the end, if we have time, I'll show you where those are. But they're all on the student schema in Redshift. We're going to focus on the student advisor history table. And this table contains one row per student per major plan. There are some advising committees assigned to minor certificates, but it's not quite. But that data is very rare, at least what I've seen in our college. So it's per major plan, per advising committee, and the focus is on undergraduates only, mostly in this table. You might find a few graduate students, but this table is mostly undergraduate centric, since most of the graduate data is tracked through other tables, like through their iPods and things like that. Contains in a student's entire advising history. That's why I wanted to note the effective date here is an effective data table. So it requires a little bit of knowledge. Some effective data tables are already max effective dated, like the profile tables, but this one is not. So it requires a little bit of ingenuity and understanding on what you're pulling back and how you can get the records that you need. What you normally do with this table is you will join it to one of the profile tables, like profile major current and or profile major term. If you're familiar with any of those tables, that provides a lot of rich data that's summarized in a single table based on, and you can use one or both of those tables on a query to get pullback data that you need. So the data in this table is very similar to the data that you can see that's in the student advisor portal in PeopleSoft. I don't know if that link works for everyone, but that's the link that when I go to the student advisor portal, that's what I see. And you can also view this data that's in this table on the Students My ASU page. Anybody have any questions at this point? Okay. So we've been using this advising data for couple of years now, but with the migration from my reports and then Oracle. So part of the migration is we moved it from moving it from Oracle, moving it from my reports to Hyperion, so the BI desktop, and then moving it from Oracle to Redshift. And so in doing so, I also want to specify, I'm sort of working backwards from the solution that I've already have. So I'm going to give you a subset of the data that we use to sort of look at the different scenarios that we found within at least our own data within the college. But keep in mind that we spent quite a few hours and quite a bit of time sort of getting the data down and summarizing sort of what I'm going to show you today. So it may look sort of simple, but this is just a very, very small subset of the larger data set that we pull back. So here's an example of, we've got 7 unique students. If you look at the student identifier on the right, all but 2 of student 6 and 7 are listed twice. And if you look at the next column, the number of committees per plan, you'll see that each of the first 5 students has 2 advising committees on the same academic plan that's located in the final column. So we can actually summarize this. So we have 1 row per student, but then we've aggregated the committee ID, which is the student's advisor. I should say, advising committee is also the student's advisor or advising committee, into one row per student based on their academic plan. So you can see that for the first 5 students, they're assigned to multiple advising committees on the same plan, and then the final 2 students just have 1 advising committee on the same plan. These are actually distinct students, even though the plan is the same. It just happened to work out that way when I randomly selected a group of students to display here. So we have actually 3 scenarios in this small subset that sort of covers almost everything that we need. So students 1, 2, and 4 are assigned to multiple but distinct advising committees on the same plan. Scenario 2 are students assigned to the same advising committee multiple times on the same plan. That's students 3 and 5 outlined in blue. And then the final 2 students were assigned to 1 advising committee per plan, students 6 and 7. So the question is, students 6 and 7 have only 1 advising committee assigned, while students 1 through 5 have multiple. Seems correct, but how do we verify our results based on what we think should be correct? Typically 1 advising committee per plan. Again, there's a lot of context and background and process that goes into this, the way the committees are assigned, and that might be unique to the college. So this scenario you may not find if you're in a different college. The scenarios you see here may not be the same as what we're finding, because our process could be different from college. The process could be different from college to college or unit to unit. So the original query, so this is going to get a little bit more technical here for those of you that are more familiar with SQL or maybe not. So hopefully hang on and we'll get to the final result quickly. So the original query uses the standard correlated subquery approach, which is generally how a lot of queries in my reports were written, where you select the maximum effective date and then you match it back to the main query section to pull back only the subset of records that you want. In this case, we only want the students' we only want the students' current advising committees. And so we do that by looking at the effective date. So there's been a lot of, so in migrating this and migrating this from Oracle to Redshift, and then sort of wanting to look and sort of explore the data a little bit, what other options do we have to maybe look at this data to see, is something correct? How do we check it? How do we validate it? So another approach that's very common here, and I don't know how many of you have done this, is using the row number method, where you can apply a row number function and then row number. So you pull back the entire data set and not just those that are with the maximum effective date here, but you apply the row numbering here. The key part to this is defining the partition. This can be a good way to remove duplicates and check for duplicates in a query. It can also be it can be somewhat easier to read if you're trying to understand someone else's SQL that they've written than a correlated subquery, but may require some trial and error using the partition by statement to get the desired or maybe correct results. So the hardest part with using this function is understanding the partition, and that requires really sort of understanding, at least at some level, the type of data you're pulling back. But I find this a very useful approach for checking data. However, so let me go back up here. So we've got this, so we sort of set up our row number and our partition similar to the way we're matching on the where clause here in the correlated subquery. This doesn't quite work. The above partition, if we go back to scenario 3 here, which is students assigned to 1 advising committee per plan, if we use a row number with this type of partition, we only return 1 advising committee per plan. And you can see here that the correlated subquery, this is a correlated subquery in the second column, which is what we did originally, that's displayed on the previous slide. And I called this row number partition 1 because you'll see we'll try a different partition to see if that will actually help us. But it's only giving us back our only 1 committee for that student and not 2. And we do know that these students do have 2 committees assigned. So let's try another partition just as a by trial and error. Sometimes you just kind of have to change your partition up to see if maybe that might help. It may not make sense. Sometimes if it doesn't make sense in your head, or, just try it anyway. Just, you throw something at the wall to see what might work. So let's throw our committee ID in the partition to see if that might help. So this only satisfies scenario 1, and it only satisfies scenario 3 for student 7. So you can see here in our original correlated subquery, it does return the second partition does return the multiple committees for the students whose committees are different. Does anybody know why that is? Does anybody know what's happening with the row number if the committee IDs are different versus if they're the same? And I don't have that here. But because we're partitioning by the committee ID for the students here outlined in red, the row number will return 1 for each of those committees. But if for students like 3 and 5 who have the same committee assigned, the row number will be 1 and 2. So we're only still returning 1 committee ID for that student, even though they do have 2, even though it's the same committee. So does anybody have an idea? Is there any other function that might provide the partition we need to satisfy our scenarios 1, 2, and 3 all at once? Does anybody have an idea or want to volunteer an answer? Any experience with this? I see some chats. Or do we have any chat questions or comments or anything so far, Zach?
Just a question about whether the slides would be available, which this session is being recorded. So the recording will be available after the data conference.
Okay. So we can use another SQL function that's very similar, and it's in the same family as a row number function called the rank, or you can also use dense rank. They really operate the same way. The syntax for the rank function is exactly the same as the row number, just instead of row number, then it's rank, and then you in your overstatement you do the partition, and then you provide your column list, and then you order by with a column list. This DESC at the end means descending. So in this case, since we want by default without the descending, then whatever your order by will order by from smallest to largest. In this case, since we want the maximum effective date, we can tell it to row number to start the numbering at the most recent effective date or the highest effective date and not the smallest. Does that make sense to everyone? So let's apply this to our query now. And so instead of using row number, this is exactly the same as the row number using the original partition, which is employee and academic plan. And then when we do that, then here are our results. Here's the original results using the correlated subquery and the new results using the rank partition. And you can see these match exactly. So our approach appears to work. And now the entire data set, again, this is a subset of 7 students, but the entire query returned 64,000 students when we run this for our list of the entire list of our current students in the college. This is applies to both immersion and online students. Why do we want to do this? So there are a couple of different reasons. The final query incorporates the final query that this data will be part of incorporates other tables that require maximum effective dating. So as you can imagine, when you're generating the SQL or trying to write this, multiple maximum effective data tables can make your SQL somewhat harder to read, can make it a little bit harder to troubleshoot. So using this row number or rank functions can actually make it a little bit easier. Rewriting the query without correlated subqueries can make the SQL more readable and understandable, which is what I just stated. So part of incorporating the rank and row numbers, we can also, so I'm going to switch gears a little bit. Sorry, there's a lot in here and it's very dense. So bear with me. So part of incorporating, because this does, again, going back to this, this first bullet point here, since we're going to be using several tables, you can apply this rank and row number type functionality in what are called common table expressions. And you can use those to replace correlated subqueries within a larger query. And I'll show you exactly what the SQL, and just to give you an example of what the SQL looks like in a correlated subquery here. Oh, sorry. Let's go back here because I actually have that already. Sorry, guys. So anyway, so you can use a CTE to replace a correlated subquery. And basically what it is it's just, you define it with it before you run your main SQL statement, you define this with statement. And then this is the table name that you're going to use within your larger query. And then I'm not going to go into why we're excluding some of these here, but then all of that ranking and everything we can do within this CTE. And then this creates a temporary table that can be used and joined to our regular query just like it would a table within the warehouse. So so whatever fields we make available in this CTE are available for us to use in our main query, and we can join it to anything like the profile tables I mentioned earlier or something else. Creates a temporary table that can be joined to the main query. Fields in the CTE are accessible in the main query. So those three things. You can also you create this CTE, you create your partitioning, and then you can, unlike with a correlated subquery, you can actually use this as a table to test your data, to validate your data as well. And it makes it a little bit easier because you can actually say a select star from Stu Advisor, say in your main SQL query without anything to pull back what's contained in this table. So you have full control over what's in the table, or you can see what's in this table. With a correlated subquery, it's sometimes difficult to do that. And because the subquery will always return sort of a reduced data set. And you're reducing your data set here, but it's a little bit easier and nicer to read. So let me show you an example of the query that we use that in. So this is the main query for pulling back our entire population. I'm not going to run this because I don't want to show the student IDs, and there are some names in here as well. But you can see the CTE here that I just displayed. And then it's used down here just as a regular table within the main query, but I'm joining it to other warehouse data here, like I'm joining it to the profile major current table. And then when I run that, then I'm getting my entire list of students who have a current plan in the college. And then if they have a major in the college, then I'm returning their advising committee. This is actually removing, we don't really want to, we're not tracking this, whether they're these are the Barrett advising committee IDs. So we're just removing those from our data set. We don't need to put those in our data set. So we're only pulling back anything that's related to the plan that's not part of Barrett, because we don't really want to report the Barrett committee IDs. They're Barrett flags, some of the profile tables we can use. We don't really care about that. So, and then here's the Alteryx workflow for some of the tables that I used, and the Alteryx workflow I used to look at the various scenarios. This is the original correlated subquery. This is using the row number partition 1 and 2 actually, and then using the rank. And then I'm joining these back just to, and so these are similar to those tables that I had in the main slide.